A warm welcome everyone. I'm Jairamar, currently working as a senior AI engineer at RBG.AI, and I'm also pursuing my PhD at Amrita Vishwavidyapeetham. Today, I'm pleased to present our work titled A Scalable Noise Robust Speech Recognition Framework for Multilingual and Low Resource Speech. So, this work is a collaborative research effort between RBG.AI Research and Amrita School of Artificial Intelligence. So, I am presenting this paper as a part of main conference at SPEEL 2025. Here is the outline of my presentation. I will begin with a brief introduction and motivation behind this work. Then I will discuss related works and formally define the problem we address. After that, I will explain our proposed methodology in detail. Finally, I will present the experimental results, conclusion, and future research directions. So, automatic speech recognition or ASR is a key technology which enables natural human-machine interaction in applications such as voice assistance and transcription-based systems and conversational AI systems. Despite significant progress, deploying ASR system in real-world environment remains challenging. So these challenges arises due to acoustic variability, such as background noises and device mismatch, and linguistic variability, such as accents, dialects, and multilingual speech. So most of the modern ASR systems are built as a monolithic end-to-end models, which limit their ability to adapt to new languages and domains and noisy conditions. Moreover, collecting large-scale annotated speech dataset for every language and condition is impractical, particularly for low-resource languages. This motivates the need for a scalable and modular ASR framework that can operate reliably under real-world constraints. So motivation and objective. So the current ASR systems perform extremely well on clean benchmark dataset, but their performance degrades significantly under noisy or multilingual and device mismatched environments. So this mismatch between a benchmark performance and real-world deployment is a primary motivation behind our work. So our main objective is to decompose ASR system into a modular component, which rather than treating it as a singular black box model. Specifically, we separate the system into an enhancer for noise robustness and a multilingual encoder for cross-lingual speech representation learning and a dynamic decoder for language and domain adaptation. So this design allows independent optimization of each component that we can enable scalable deployment across languages, domains, and hardware platforms. So to give you a brief about related works, so we know that early end-to-end ASR models such as deep speech and wave to letter simplified these traditional pipelines by directly mapping audio to text. However, these systems are monolithic, making it difficult to adapt them to a new noise conditions or devices or languages without extensive retraining. And there are other approaches such as multitask learning approaches attempted to jointly perform speech enhancement and speech recognition, but they require paired clean noise dataset, which often fail to generalize to unseen noise types. Apart from this, we do have other approaches like waveform-based enhancement models, such as WaveUnit and DMOCus, which significantly improve speech quality, but they operate mainly as a front-end modules rather than a complete multilingual ASR pipeline. So other approaches such as self-supervised models like Wave2Vec2 and Conformer have further advanced this ASR by learning strong speech representing from large-scale dataset. However, these models are primarily optimized for resource-rich languages and require significant computational resources. Recent systems such as Whisper demonstrate impressive multilingual robustness, but they rely on massive weakly supervised dataset, which are not designed for lightweight or edge deployment. Overall, existing approaches either lack modularity and are resource intensive and do not explicitly address low resource multilingual setting in a scalable manner. So let's move towards our problem definition. So formally, we consider a supervised speech dataset which contain multiple sources of variability, such as noise, language, accents, and domain, and combination of all these things. So traditional ASR system basically aims to learn a single function that maps raw speech directly to the text. So in contrast, our approach decomposes this mapping into three distinct stages which is enhancement and encoding and decoding. So this decomposition basically allows each source of a variability to be handled explicitly, resulting in improved robustness and adaptability across real-world conditions. So we evaluate our framework on both resource-rich and resource-poor languages. For English, we use LibriSpeech as a standard benchmark, and for Libri-Adapt to evaluate robustness across different devices. And for Tamil, which is a low resource language, we use Common Voice Tamil dataset and also the Microsoft Tamil Speech Corpus. We also introduce synthetic noise dataset such as rain, wind, and laughter to evaluate robustness under realistic acoustic condition. Now I will explain the methodology of our proposed framework in detail. So the key idea behind our approach is to decompose automatic speech recognition into modular components rather than relying on a single monolithic end-to-end model. This decomposition allows us to independently address noise robustness, multilingual representation learning, and language-aware decoding, which is particularly important for low resource and real-world deployment scenarios. So the first component we do have this enhancer, so which operates directly on raw speech signal. So the goal of the enhancer is to reduce acoustic variability before recognition so that the downstream encoder receives a clean and a standardized input. So we begin with the signal uniformization step. So all incoming audio is resampled to 16 kilohertz and then converted to single mono channel and represented using 16-bit PCM format. So this step is crucial because speech data collected from different devices such as mobile phones, USB microphones, or array microphones often differs in sampling rate and bit depth and channel configuration. So by enforcing this common signal representation, we remove device-dependent artifacts and ensure consistency across dataset and recording conditions. So after uniformation, we apply noise suppression using demarkers, a waveform domain neural networks. Unlike traditional spectrogram-based enhancement methods, demarkers operates directly on the time domain waveform. So this allows us to effectively handle non-stationary and real-world noises such as rain, wind, background chatter, and environmental sounds that commonly appears in conversational speech. Importantly, this enhancement is performed independently of the ASR model, which means the enhancer has been improved, can be improved or replaced without retraining the entire system. Following the noise suppression, we apply voice activity detection to remove long silence regions and non-speech segments. So this step serves two purposes. First, it introduces unnecessary computation of First, it reduces unnecessary computation by eliminating uniformity frames. Second, it helps the encoder focus on linguistically relevant speech regions, which improve recognition accuracy, especially in noisy recordings. So the second component of our framework is the multilingual wave-to-vector encoder. So this encoder is responsible for transforming enhanced speech into high-level acoustic representation. So why wave-to-vector? So we select wave-to-vector because it is self-supervised learning framework, which is capable of learning rich speech representation from large amount of unlabeled audio. So this property is particularly valuable for low-resource languages where labeled data is scarce and expensive to obtain. So the pre-trained multilingual encoder is fine-tuned using Tamil speech data, considering both native Tamil script as well as transliterated Tamil script. So we use CTC loss, which allows us to train the model without explicit frame level alignment between audio and text. By sharing the same encoder across multiple languages, the model learns language agnostic phonetic features, which basically enables effective transfer from resource rich languages such as English to resource poor languages such as Tamil. Finally, we have our third component, which is dynamic decoder. Basically, it handles the language structure and domain specific constraints. So the encoder outputs are decoded using the CTC beam search, which explores multiple hypotheses rather than relying on a greedy decoding. So basically, this helps recover correct word sequence, especially in noisy or ambiguous condition. So along with that, we also integrate a modified kernel language model during the decoding process. So the language model basically provides linguistic probability scores, which guide the decoder towards grammatically and contextually valid word sequence. So this result is substantial reduction in word error rate across both clean and noisy conditions. So the key novelty or like the key aspect of our decoding part is that so language and script aware decoding. So during the decoding, we also perform word level language identification in order to distinguish between the English and Tamil tokens. So this is particularly important for the code mixed speech, which is common in Indian conversational setting. So for Tamil outputs, we use structured perceptron-based back transliteration model. So basically, that model allows the system to output native Tamil script or maintain transliterated text depending on the application needs. So this makes the framework flexible and script independent, which is actually crucial for multilingual deployment. So to summarize our methodology, so we basically propose a decomposed ASR framework into a noise robust enhancer and a shared multilingual encoder and a dynamic language aware decoder. So this modular design basically enables scalable adaptation and improved robustness and practical deployment for this multilingual and low resource speech recognition. So next we'll move towards the results. So first, on the LibriSpeech benchmark, our system achieves comparable word error rate to conformer large on clean speech, despite not being trained directly on the LibriSpeech transcripts. Next, on Libri-Adapt, which evaluates device variability, our model shows a five-fold reduction in word error rate compared to the baseline systems of Libri-Adapt. So these results clearly demonstrate the effectiveness of our enhancer module in handling acoustic and channel variability across different device settings. So this slide basically shows the result on Tamil speech. Basically, it compares transliterated and native script decoding with and without the noise, as well as with and without the language models. So we observe that the language model significantly reduce the word error rate, so especially in noisy conditions. And native script decoding consistently outperforms transliterated decoding, so which basically achieves around 19 to 20% of word error rate on common voice Tamil. So even under added noise such as rain, wind, and laughter, performance degradation is minimal. So overall, our framework achieves nearly 2x improvement over the previous best systems. So basically, it demonstrates strong linguistic robustness in low resource settings. So to conclude, we propose a modular ASR framework that explicitly separates noise handling, multilingual encoding, and decoding. So our system basically shows strong performance across clean benchmarks, noisy device conditions, and low resource multilingual settings. So this modular design allows targeted adaptation without retraining the entire system. So in the future, we plan to extend this framework to more Indian and Dravidian languages to integrate neural language models and to further optimize the system for edge ready and real time deployment. So these are some of the key references we utilized for this slide, and thank you.